Hello again, and welcome back to The Lazy Scientist. Whether you've arrived looking to relax, to drift off after a long day, or simply to let your thoughts float out into the quiet night sky, you've found the right place. Tonight, we're setting out on a journey that began in 1977, when two small spacecraft lifted away from Earth, carrying with them a fragile cargo of instruments, fuel, and an almost unreasonable amount of optimism. Those spacecraft are still out there, pressing farther into the dark than any machine built by human hands has ever traveled. This is the story of the Voyager missions, a story woven with discovery, imagination, and a very human attempt to whisper hello into the universe. Before we get underway, I'll ask a small favor. If these sleepy explorations keep you company, a like or a subscribe helps more than you'd guess, both for a lone spacecraft still singing across ancient radio waves and for a narrator sharing science in the quiet hours. Tell me, too, where you're listening from. Are you in a bustling city still buzzing at midnight, or a quiet village winding down under starlight? As always, I hope this story isn't too interesting, but if it keeps you awake, at least you'll carry with you new wonders about interstellar space, magnetic fields, and golden records. So settle in, breathe easy, and let's follow Voyager into the unknown. The 1960s and early 70s were years of contrast. The world was filled not with calm, but with the tension of a Cold War. A competition balanced uneasily between fear and fascination. The United States and the Soviet Union measured each other across oceans and across ideology, locked in a contest for dominance that extended beyond politics and into the heavens. Yet in this rivalry, something extraordinary unfolded. Space stopped being only a strategic prize. It became a stage for imagination. In 1969, humans set foot on the moon. It was a breathtaking instant, flickering across television screens in grainy monochrome, yet grand enough to pause the world. For a heartbeat in history, the planet held its breath as Neil Armstrong and Buzz Aldrin moved across lunar dust. That moment belonged not only to America, but to humanity, one of the rare times when the phrase, "we did it," truly meant all of us. But after the flag was planted and footprints pressed into lunar soil, a strange fatigue set in. The moon was conquered, so what next? Returning again and again didn't feel the same. Public excitement dimmed. Budgets shrank. Missions were canceled. NASA had reached the highest peak and now stood looking out, wondering where else to climb. It didn't take long to spot the next horizon. Beyond the orbit of Mars sat a kingdom of giants: Jupiter, Saturn, Uranus, Neptune. Massive worlds cloaked in mystery. Banded storms, glittering rings, moons that hinted at hidden secrets. They were beautiful, enigmatic, and for centuries unreachable. But by the 1970s, rockets had grown stronger, electronics smarter, and engineering confidence higher. The giants, while still distant, no longer felt impossible. There was one enormous challenge. The outer planets weren't just farther than Mars, they were staggeringly far. Reaching even one of them demanded incredible planning, precision, and patience. Reaching all four? That was the kind of proposal that made engineers set down their coffee and ask if someone was joking. Yet the universe has its moments of kindness. Roughly once every 175 years, the four outer planets align in such a way that a single spacecraft could visit them in sequence, using each planet's gravity as a slingshot to fling itself onward. Imagine a cosmic game of hopscotch, Jupiter lending a tug, Saturn hurling the craft further, Uranus pushing it on toward Neptune. The mathematics weren't new. But the timing was exquisite. The late 1970s offered this rare celestial choreography. If NASA wanted to attempt the greatest tour ever undertaken, the clock was ticking. They called it the Grand Tour. Born in the optimism of the 60s, it was at first a lavish dream of 4 separate spacecraft traveling to every giant planet and even Pluto. It was bold, breathtaking, and absurdly expensive. As Apollo ended and politicians reached for their calculators, the Grand Tour was quietly shelved. Yet the dream itself did not fade. It simply reshaped. And so Voyager was born. Instead of 4 extravagant probes, NASA would build 2. Identical twins, each carrying the same instruments, each following slightly different paths. Robust enough to endure, clever enough to adapt, and cheap enough to get through Congress. Expectations were modest. The goal was Jupiter and Saturn. Anything more would be considered a bonus. Few believed they would function more than 5 years. In the cultural backdrop of disco, bell-bottoms, and rotary phones, work began on machines that would endure longer than any spacecraft ever has. It was not a simple task. Remember, this was the 1970s, an era when a digital wristwatch was futuristic. Voyager's computers held less power than the simplest gadget you carry today. By comparison, your phone's weakest app dwarfs their entire memory. And still, engineers carved brilliance out of limitation. The first problem was power. Solar panels, the workhorse of satellites, were useless when sunlight dwindled to a feeble glow. Instead, engineers turned to radioisotope thermoelectric generators, small nuclear power sources that transformed the heat of decaying plutonium into steady electricity. Compact, efficient, and long-lasting, they promised decades of life. Each spacecraft would carry 3 of these units, glowing silently, feeding power into circuits that had to last longer than most marriages. Next came communication. Across billions of miles, even the strongest signal fades into whispers softer than the static of a detuned television. To bridge the void, Voyager needed a wide, high-gain antenna, and Earth needed the deep space network. Colossal radio dishes built to capture echoes fainter than imagination. Through those faint pulses would come photographs, measurements, and even something more profound: the quiet voice of Earth itself. That voice was not left to engineers alone. Enter Carl Sagan and a committee of dreamers who asked, if Voyager might one day be found by someone not of this Earth, what should it say? Their answer was the golden record, a gold-plated disc etched with music, greetings in dozens of languages, sounds of our world, and even the electrical traces of a human in love. It was less instruction manual and more poem, a declaration that we existed, that we had loved, laughed, sung, and tried to say hello. As the spacecraft came together in NASA's Jet Propulsion Laboratory, excitement spread quietly but deeply. Unlike the spectacle of the moon landings, Voyager's promise was slower, subtler. These probes wouldn't carry humans. Instead, they carried everything we had learned: our science, our art, our ambitions. They were time capsules of a divided but still dreaming civilization. In the face of political turmoil, economic stress, and technological limits, they reflected our best side: curiosity, endurance, and the need to explore even when no one is watching. Back then, interstellar space belonged to science fiction. The outer planets were just dots. Neptune was a name on a chart, Titan a faint blur. The edge of the solar system wasn't even well defined. And yet, the belief was unshakable. We could go there. With math, patience, and duct tape, maybe even luck, we could build something that outlasted us. Something that, in its silent journey, carried the best fragments of what it means to be human. By the mid-70s, the launch window neared. Teams worked around the clock, wires checked and rechecked, instruments tested, commands rehearsed. Scientists plotted trajectories, engineers calibrated cameras, and artists selected the images that would accompany humanity's emissary. The Voyager spacecraft were as much poetry as plumbing, as much daydream as data table. They weren't born out of triumph so much as out of longing, the urge to keep reaching outward after we had touched the moon. And maybe that's why Voyager still resonates. Amid all the noise of our world, the probes remind us of something quieter and steadier. The patient heartbeat of curiosity, the question that never leaves us, what's out there? As the rockets were readied, the cameras secured, and the golden records bolted into place, the Voyagers stood waiting. Twin travelers who would never return, but who would forever remind us what it means to leave. Designing something to endure 4 decades in deep space is bold under any circumstance. Designing it in the 1970s, with no repairs possible, no pit stops, and no second chances, that wasn't just bold, it bordered on fantasy. Yet that was precisely what NASA's engineers set out to do when they began assembling Voyager. Their task was clear but daunting. Build 2 robotic explorers that could withstand the violence of launch, survive the void, examine worlds humanity had never seen in detail, and then keep going, transmitting data long after most expected them to fall silent. The first hurdle was durability. Space is not gentle. It is unimaginably cold, hundreds of degrees below freezing, and laced with radiation, cosmic dust, and surges of charged particles fierce enough to fry delicate electronics. Voyager didn't need to be sleek or fast. It needed to be stubborn, the kind of machine that could take a beating and keep working. At its heart was a sturdy aluminum frame designed to endure both the brutal shake of launch and the endless hazards of interplanetary travel. From this core extended booms, sensors, cameras, and most famously, that great white dish, the high-gain antenna, nearly 3 meters across, a gleaming satellite dish sculpted for a cosmic role. That dish became Voyager's voice. Every image, every measurement, every whisper of data would funnel through it, traveling back to Earth as signals so faint they were weaker than the static of an untuned television. Yet even across billions of miles, the immense radio dishes of the Deep Space Network could pluck those signals from the noise, decoding them into pictures and numbers that told us what Voyager had seen. Today, when Voyager speaks, it does so with a power measured in billionths of a watt, and still we listen. Inside the spacecraft, the brain was modest, even for its time. Each Voyager carried about 69 kilobytes of memory. Not megabytes, kilobytes. You could store Voyager's entire computing capacity on a single floppy disk, with enough room left over for a short recipe and a pixelated game. A single photo on your phone today requires more storage than the Voyagers had in total. And yet, those tiny computers were built with resilience in mind, hardened against radiation. Simple in design and programmed to operate without constant human oversight, they embodied reliability. Communication was never quick. Commands from Earth took hours to arrive, and responses took hours to return. If a problem arose, engineers had to diagnose it slowly, patiently, as if tending to a faraway patient who could only whisper once a day. This delay demanded simplicity. Voyager couldn't rely on fast fixes or last-minute rescues. It had to be trusted to make basic decisions on its own. Power posed another immense challenge. Beyond Jupiter, sunlight dwindles into a pale memory, too weak to feed solar panels. So NASA chose something different: radioisotope thermoelectric generators, or RTGs. These compact devices turned the heat of decaying plutonium-238 into electricity. Each Voyager carried 3 of them, producing about 470 watts at launch. Less than a household microwave, but steady, reliable, and enduring. Decade by decade, as the plutonium cooled, power output declined. Managing Voyager's energy became like running a cabin on a dying generator, deciding which lights to keep on, which appliances to shut off, and which comforts to forego. Every year since, engineers have had to make hard choices about which instruments could remain alive and which had to be powered down forever. Still, those instruments were carefully chosen to begin with. Each spacecraft carried 10 major devices: cameras to capture images of planets, spectrometers to analyze light, magnetometers to sense invisible fields, detectors for plasma and cosmic rays. None of them were glamorous by modern standards, yet together they formed an orchestra capable of revealing the hidden structure of the outer solar system. Voyager's cameras, though primitive compared to even the cheapest phone today, captured storms swirling over Jupiter, volcanoes erupting on Io, and Neptune's haunting blue face. These pictures weren't just scientific data, they were icons, reshaping how we imagined the planets. All of this technology, of course, was strapped atop a Titan IIIe Centaur rocket, a brute of a machine built to hurl payloads across the solar system. In August and September of 1977, the twin probes, Voyager 2 first, Voyager 1 second, roared off the launch pad at Cape Canaveral. Their destinations were not entirely certain. The alignments were precise, but the future was not. Voyager 2 would take the slower route, giving it a chance to reach all 4 giants. Voyager 1, faster and aimed higher, would focus on Jupiter and Saturn, and on a close encounter with Saturn's moon, Titan. The launches themselves were unassuming compared to Apollo. There were no astronauts waving from the capsule, no global countdown watched by millions. Instead, there were engineers holding their breath in control rooms, scientists clutching datasheets, and a scattering of reporters scribbling notes. These weren't missions designed for spectacle. They were designed for patience. Their drama would unfold not in minutes, but across years and decades. Yet tucked inside those spacecraft was something that transcended engineering: the golden record. As Carl Sagan's committee debated what to include, they faced the strangest editorial challenge in history. If you could speak for Earth, what would you say? The answers were as varied as humanity itself. Greetings in dozens of languages, music from Bach to Chuck Berry, the sound of wind, of waves, of laughter, a kiss, a mother's voice, the crackle of fire, the roar of a rocket, even the brainwaves of a young woman in love. Encased in gold-plated copper, protected for 1 billion years, the record was not just data. It was a time capsule, a message, a bottle cast into the cosmic sea. We were here. This is us. Back on Earth, the work continued. Every wire checked, every sensor calibrated, every command sequence rehearsed. The Voyagers were not flashy. They had no astronauts to cheer from the capsule window. What they carried was subtler, but in its way, more profound. Our curiosity crystallized into metal and circuitry. They were machines built during a divided era, amid inflation, uncertainty, and abstracts and cultural upheaval. And yet they represented our best selves, the part of us that refuses to stop wondering. By 1977, few people outside the space community even knew the names Voyager 1 and Voyager 2. And yet, in the long view of history, they would become more enduring than most presidents, wars, or cultural icons of the decade. They were not designed to return. Their destiny was to leave, to slip away from the cradle of Earth, wander past the giants, and drift into interstellar night, carrying the echo of who we were. And so they launched, twin emissaries of humanity, modest in design, fragile in appearance, yet extraordinary in their endurance. Decades later, as their signals still whisper across space, we know how much was built into them. Not only the mathematics and engineering, but the poetry of ambition, the hunger to know, and the fragile hope that someone, somewhere, might one day hear their call. In the end, the story of Voyager is not only about spacecraft, it is about us, about the quiet insistence that even when our budgets shrink, even when interest wanes, even when the world is preoccupied with its own quarrels, there is always a part of humanity that looks outward. That part built Voyager. That part gave it a voice. And that part still listens today across the endless dark for the faint sound of our own curiosity echoing back. One of the cleverest features hidden within Voyager's design was its magnetometer boom. At first glance, it looked like a simple extending arm, but its brilliance lay in holding the sensors far from the spacecraft's own magnetic influence. By pushing the instruments out into the void, the probes could measure the invisible lines of magnetic force flowing from planet to planet without contamination from their own machinery. This single design choice gave humanity its first real chance to sense the faint edge of the heliosphere, the great bubble of solar wind that surrounds our system, and to discover where that wind gives way to the true interstellar medium beyond. Radiation shielding was just as vital. Space is not gentle, but Jupiter in particular is brutal. Its magnetic field is so powerful, it makes Earth's look laughably weak. The difference between a fridge magnet and a roaring electromagnet. Without protection, Voyager's delicate electronics would have been fried in an instant. To defend them, engineers wrapped sensitive parts in shielding and tucked them into the safest compartments of the spacecraft's body. Voyager wasn't invincible, but it was given armor enough to stand a chance. For all this complexity, there was elegance in its simplicity. Voyager wasn't built to land or bring anything back. It had no legs, no parachutes, no extra computer waiting to take over if something failed. Its mission was straightforward: fly past, observe, send the results home, and keep going. That clarity allowed the team to pour their effort into precision rather than redundancy. Every connection, every solder joint, every wire was scrutinized. The probes were assembled inside spotless clean rooms where even dust and human breath were carefully controlled, because perfection wasn't just preferred, it was survival. Navigation was its own quiet marvel. Today, we take for granted real-time GPS tracking, but Voyager had no such luxury. Instead, it oriented itself using gyroscopes and star trackers, aligning with the sun and familiar constellations. Patiently, methodically, the spacecraft would rotate to aim its cameras, perform its measurements, and then turn back to face Earth, so the precious data could be sent across space. There was a kind of politeness to its rhythm, always remembering to check in before continuing on. Even the threat of high-speed debris was considered. Space may be empty, but it is never truly empty. A pebble the size of a grain of rice, moving at thousands of miles per hour, could spell disaster. Voyager wasn't armored like a tank, but its vital organs were shielded behind protective panels. The odds of collision were small, yet every day the spacecraft endured was, in its own quiet way, another victory. And then there was Voyager's almost nostalgic charm, its fundamentally analog nature. Commands from Earth weren't sent through slick interfaces. They were transmitted as binary strings, lines of code beamed through space. Images were not instant photos, but streams of data, arriving line by line, sometimes over days. It was slow, but it worked, and remarkably, it still works. The beauty of Voyager's story isn't only its longevity, but the ingenuity of building something so capable with the limited tools of its time. No smartphones, no cloud servers, no sleek CAD programs. Just pencils, paper, punch cards, soldering irons, and oscilloscopes. From those humble means emerged machines that still speak to us nearly half a century later. Their design was not flashy, but it was sturdy and purposeful. Every nut, bolt, and line of code represented a belief that exploration matters, even if no human is there to witness it directly. Year by year, the Voyagers grew quieter, their instruments dimmer, but they endured. They drifted, they hummed, they sent back whispers from the void. They became testaments, not only to brilliant engineering, but to the stubborn idea that curiosity deserves to outlast us. By the late summer of 1977, the two spacecraft stood ready on separate launch pads in Florida. Identical in their build, identical in their mission, they waited for their chance to slip the bonds of Earth. They were Voyager 1 and Voyager 2, siblings set to travel farther than anything humanity had ever created. But spaceflight, like most great adventures, does not always follow neat numbering. Voyager 2 actually launched first on August 20th, 1977. Voyager 1 followed just over 2 weeks later on September 5th. The numbering had nothing to do with who left the ground first. It had everything to do with their trajectories. Voyager 1's path would take it to Jupiter and Saturn more quickly, so it earned the title of first, despite being the second to leave. It's a little confusing, but space history has always had a taste for poetic license. Still, the true marvel wasn't in the order of their launches. It was in what they were attempting. These weren't just missions to a single distant planet. They were missions to visit several, one after the other, in a kind of planetary relay race. Each encounter would fling the spacecraft faster and farther onward, carrying it deeper into the solar system. This was possible only because of a rare planetary alignment, a celestial choreography that happens just once every 175 years. In this brief window, Jupiter, Saturn, Uranus, and Neptune lined up in such a way that a single spacecraft could use each one as a gravitational springboard. The technique called gravity assist was one of the cleverest maneuvers in space exploration. Instead of burning unimaginable amounts of fuel to chase each planet, the spacecraft would borrow momentum from the giants themselves. Imagine swinging around a moving train. The moment you grab on, it pulls you forward, flinging you off in a new direction with speed you never had before. That's what Voyager would do. Not once, but again and again. But such a trick required exquisite timing. Launch too early or too late, and the whole cosmic highway closed. The window was tight. Voyager 2, taking the longer path, had to leave first. Its route gave it the chance, if it survived long enough, to reach not only Jupiter and Saturn, but Uranus and Neptune as well. Voyager 1 would move more quickly, reaching Jupiter and Saturn first, and then turning sharply upward, away from the plane of the solar system. Each path was different, but together they formed a tag-team exploration, two emissaries handing off humanity's gaze as they moved outward. The launches themselves were modest compared to the dramatic spectacles of Apollo. No astronauts waving, no worldwide countdowns. Instead, there were anxious engineers, silent control rooms, and rockets primed to carry fragile explorers into the dark. Each Voyager was mounted on a Titan IIIe Centaur rocket, a heavy lifter designed for interplanetary missions. These launch vehicles were beasts of precision and power. Multi-staged machines that could push their fragile cargo far beyond Earth's pull. Voyager 2's flight on August 20th wasn't flawless. Its upper stage briefly lost telemetry, but the spacecraft itself quickly stabilized. Voyager 1's launch, just 16 days later, was cleaner, almost routine. Within hours of both departures, two small probes were on their way, their trajectories locked, their fates sealed. From the moment they slipped past the atmosphere, they were already different from any spacecraft that had flown before. They weren't designed to orbit a planet and stay. They weren't designed to return samples or parachute back to Earth. They were Voyagers in the truest sense, meant to keep going, never stopping, never turning back. What they carried was endurance, ambition, and the chance to ride a gravitational highway only briefly open to us. To fully grasp how miraculous this highway was, it helps to picture the physics at play. As Voyager approached a planet, it fell into that planet's gravitational well, speeding up as though it were being reeled in by an invisible rope. But instead of crashing or being captured in orbit, the probe curved around, escaping on the other side with a burst of momentum it hadn't had before. Relative to the Sun, it was now faster, on a new path, directed toward the next target. Nothing was stolen from the planet itself. At least not in any measurable way. It was more like a subtle handshake, a transfer of energy so slight the planet never noticed, but the spacecraft depended on entirely. Without gravity assists, Voyager's journey would have been impossible. The fuel required to cross such distances would have made the spacecraft too heavy to launch. Instead, the planets themselves became fuel. Giant trampolines flinging the probes deeper into the solar system. But this maneuver wasn't something that could be improvised mid-flight. Every trajectory had to be calculated years in advance, down to fractions of a degree. A single error at Jupiter could mean Saturn was forever out of reach. The navigation team had to be precise, deliberate, and patient. Once Voyager was set on its course, there were no second chances. And these flybys weren't just pit stops for momentum. They were the core of the science mission. Each pass offered days and weeks of careful observations. The camera had to be aimed, exposures planned, and command sequences loaded into the onboard computer months in advance. Every maneuver had to be executed on schedule because there was no time for last-minute adjustments. The commands were sent like a choreographed routine, each step unfolding on cue, with Earth waiting helplessly for confirmation that the dance had gone as rehearsed. Voyager 1, racing along its faster path, was destined to be the first to exit the planetary neighborhood of the solar system. But that same trajectory meant it would not continue on to Uranus or Neptune. Voyager 2, slower but steadier, had the chance to visit all four gas giants, provided it survived long enough. Originally, the mission was officially committed only to Jupiter and Saturn. Everything after that was considered a bonus round. The fact that both spacecraft exceeded those modest promises is what makes their story almost mythic. In 1977, though, none of that was certain. What NASA had in hand were two machines, a fleeting alignment of planets, and a great deal of faith. The launches themselves didn't carry the spectacle of Apollo. There were no crowds watching men ascend to the moon, no prime-time broadcasts with the world holding its breath. Instead, the Voyagers began quietly, without fanfare. slipping into the night sky. Yet in that quiet, something profound was set in motion. These two spacecraft would go farther, last longer, and reveal more than anyone dared to hope. The irony of their legacy is that the greatest space mission in history began with so little attention. No fireworks, no triumphant speeches, just rockets igniting, numbers scrolling across control room monitors, and two silent machines leaving Earth forever. What followed was the grandest tour humanity had ever attempted, made possible only because, once every century and a half, the solar system opens a narrow passageway through its giants. In 1977, we stepped into it. As Voyager drew closer to its first destination, Jupiter, the reality of what these machines could do began to unfold. Jupiter had long been the crown jewel of the solar system. Massive, striped with mysterious colors, topped with the blurred scar of the Great Red Spot. Astronomers had studied it for centuries, but always from afar, through telescopes that could only hint at its true nature. Now, for the first time, we were about to see it up close. In March of 1979, Voyager 1 swept within roughly 350,000 miles of Jupiter's cloud tops, about the same distance as Earth's moon. Only months later, in July, Voyager 2 followed on a similar path. Together, they turned Jupiter from a painted blur into a world alive with detail. The first shock was motion. From Earth, Jupiter's bands seemed calm, even stately. Up close, they were chaos. Storms raged everywhere, swirling ovals the size of continents. Jet streams racing in opposite directions. Clouds twisting in patterns of dazzling complexity. And dominating it all was the Great Red Spot, no longer a simple smudge, but a churning vortex of ammonia, clouds large enough to swallow Earth whole. Its colors shifted in subtle tones, its edges rippled with turbulence, its form alive in a way no telescope could reveal. And then came the surprises. Dozens of smaller storms dotted the atmosphere, spinning, merging, breaking apart. Jupiter was not serene, but ferocious, a giant whose face was constantly remade by winds and lightning. Its size alone defied comprehension, 11 times Earth's width, 300 times its mass. A Jovian day lasted less than 10 hours, its rapid spin stretching the clouds into endless bands and fueling storms that could rage for centuries. But perhaps the most remarkable revelations weren't in the clouds at all. They were in the companions that circled this enormous world. Moons that turned out to be stranger, more dynamic, and more alive than anyone had dared to expect. Before Voyager arrived, Jupiter's moons were thought to be little more than frozen rocks, perhaps cratered like our own moon, interesting but not spectacular. What the spacecraft actually revealed was a family of worlds bursting with personality, each one rewriting expectations. Take Io. Voyager 1's cameras caught plumes erupting into space, towering fountains of molten material shooting hundreds of miles above the surface. These weren't gentle geysers of gas or dust, but volcanic eruptions, the first ever observed beyond Earth. Io wasn't dormant or still. It was alive, angry, reshaping itself before our eyes. Its surface was a riot of colors: sulfur yellows, iron reds, volcanic blacks, like an alien pizza bubbling in real time. This discovery shattered assumptions about what a moon could be. The culprit was tidal heating. Io, caught in a relentless tug-of-war between Jupiter's immense gravity and the poles of Europa and Ganymede. The constant flexing kneaded the interior like dough, melting rock and driving relentless volcanism. Earth's moon quietly reflects sunlight. Io throws fiery tantrums in orbit. Then came Europa. At first glance it seemed calmer, an icy sphere, pale and smooth compared to Io's chaos. But smoothness in the cosmos is suspicious. It usually means renewal, a surface erased and remade. Voyager's images showed dark streaks etching the ice, like scars across a frozen sea. These weren't cracks in rock, but fractures in ice, suggesting a crust floating atop something deeper. Beneath miles of ice, scientists realized, might lie a vast salty ocean, warmed by the same tidal forces that tormented Io. A hidden sea shielded from space, rich in potential chemistry. Suddenly, Europa was not just a moon, but one of the most promising places to search for alien life. Ganymede and Callisto joined the story with their own distinct characters. Ganymede stunned scientists as the largest moon in the solar system, even bigger than Mercury, with hints of a magnetic field and a strange grooved terrain that hinted at tectonic activity. Callisto, older and battered, looked like an ancient relic. Its surface was cratered nearly to saturation, possibly unchanged for billions of years. Each moon seemed to tell a new tale, transforming Jupiter from a lone gas giant into the heart of a miniature solar system. Back at Jupiter itself, Voyager turned its instruments to the planet's immense magnetosphere. This was no ordinary magnetic field. It was 20,000 times stronger than Earth's, stretching millions of miles, a vast invisible bubble of radiation so intense that unshielded electronics would have fried instantly. If human eyes could see it, Jupiter's magnetosphere would have loomed in Earth's night sky, larger than the moon. Within it raged storms of trapped particles, auroras blazing at the poles, lights akin to Earth's northern and southern displays, but magnified into titanic storms of energy. Voyager captured these shimmering arcs, proof that Jupiter's invisible environment was as dynamic as its visible clouds. And then there were the rings. Saturn may be famous for them, but Voyager uncovered that Jupiter, too, had faint, dusty rings. They were thin, dark, and easily missed, likely formed from debris knocked loose when micrometeorites struck small inner moons. Almost invisible, they nonetheless proved that ring systems were not unique, and that the outer planets all had their own jewelry of ice and dust. By the time both probes completed their flybys, Jupiter had been transformed in human understanding. It was not merely a stormy gas giant, but a complex ecosystem, with moons as strange and fascinating as planets in their own right. What had once been a blurry image in telescopes became a world of erupting volcanoes, hidden oceans, magnetic leviathans, and delicate rings. Voyager didn't just confirm what astronomers suspected, it revealed wonders no one had imagined. Volcanoes spewing fire across alien skies, icy shells hiding possible seas, moons that seemed to breathe, and moons frozen in time. All of it delivered by two small spacecraft, carrying less computing power than a modern pocket calculator. And then, almost seamlessly, the stage shifted. If Jupiter was all violence and drama, Saturn was elegance, graceful, photogenic, iconic. Even people with little interest in astronomy could recognize it instantly, wrapped in its shimmering halo of rings. Galileo first glimpsed them in the 1600s, though his telescope left him confused. He described them as ears sprouting from either side of the planet. Over centuries, better optics revealed the truth. A flat, pointy, and evenly rounded, like a pocket calculator. Vast ring systems so thin and orderly, it seemed impossible. By the time Voyager arrived in the early 1980s, Saturn was already the poster child of cosmic beauty, adorning textbooks and sci-fi artwork alike. But even the most detailed illustrations couldn't prepare anyone for the real thing. Voyager 1 swept past in November 1980, passing within 77,000 miles of Saturn's cloud tops. Voyager 2 followed in August 1981, coming even closer. Together they delivered views unlike anything seen before. A planet and its rings not just beautiful, but intricate, alive, full of patterns and mysteries. The rings were immense, over 200,000 miles across, yet astonishingly thin, often just tens of feet thick. To picture it, imagine stretching a sheet of paper across an entire football stadium. Within that fragile geometry existed countless structures, thousands of ringlets, sharp gaps, and subtle waves. Long-known features like the Cassini division, once thought empty, turned out to be filled with faint, delicate bands. Voyager also discovered the Encke Gap, a narrow split inside the A-ring, and revealed the mischievous role of shepherd moons, tiny satellites whose gravity herded particles, carving edges and sculpting ringlets with invisible hands. Even stranger were the spokes, ghostly radial streaks drifting across the rings like shadows. Their cause remains debated, possibly magnetic effects, possibly impacts stirring clouds of fine dust. Whatever their source, they gave the rings an eerie, almost supernatural quality, as though Saturn itself were whispering secrets in patterns of ice and dust. Saturn itself proved no less captivating. Its golden hues were calmer than Jupiter's wild stripes, but its atmosphere was hardly still. Bands of clouds circled in rapid rotation. Storms raged, and near the poles lurked a mystery. Hexagonal patterns etched into the clouds. Voyager spotted hints of the bizarre six-sided storm at Saturn's North Pole, though its full structure wouldn't be revealed until the Cassini mission decades later. Still, even this glimpse reminded scientists that Saturn, too, was full of surprises beneath its serene exterior. Among Saturn's many moons, none captivated the imagination, quite like Titan. Larger than Mercury, shrouded in a thick orange haze, Titan stood apart as the only moon in the solar system with a dense atmosphere. Voyager's instruments revealed that this atmosphere was mostly nitrogen, with traces of methane and hydrocarbons, eerily reminiscent of Earth's own air. For the first time, humanity encountered a place beyond our world where the atmosphere was not a whisper-thin veil, but a heavy, sustaining blanket. But the haze was impenetrable. Voyager's cameras could not see the surface. Titan was coy, revealing its chemistry, its size, and its atmospheric pressure, but keeping its face hidden. Still, scientists were entranced. A moon with an atmosphere thick enough to sustain weather could hold rivers, lakes, even seas of methane or ethane. Perhaps erosion had shaped valleys or carved shorelines. Was Titan a frozen Earth, caught in deep time, or a glimpse of Earth's distant future? The questions were tantalizing, the answers withheld behind the haze. Voyager 1's encounter with Titan was so important that it shaped the rest of its journey. To study the moon closely, the probe had to follow a trajectory that swung it out of the plane of the solar system, ending its planetary tour after Saturn. Voyager 2, in contrast, bypassed Titan and stayed on course toward Uranus and Neptune. It was a calculated trade-off, one spacecraft diving deep into Saturn's most enigmatic moon, the other preserving the opportunity to extend humanity's reach farther than ever before. Saturn's other moons, though less famous than Titan, added richness to the story. Mimas bore a massive impact crater that made it resemble the Death Star. Tethys and Dione displayed icy cliffs and valleys carved into their surfaces. Enceladus gleamed with a startling brightness, its icy surface reflecting sunlight like fresh snow. At the time, its true wonders, geysers and a hidden ocean, were unknown, yet even Voyager's first look hinted that something unusual was at work. Each moon carried scars and secrets, reminders that even small worlds could play big roles in the drama of the outer solar system. The encounters with Saturn lasted only weeks, brief flashes after years of travel, but what they revealed was profound. Saturn was no longer a distant, decorative jewel, but a complex system alive with motion and mystery. Voyager gave the planet and its moons depth, texture, and voice. And as the probes drifted onward, Saturn faded into the rear view, its golden rings now etched into human memory through grainy but unforgettable photographs. Voyager 1, its planetary work complete, tilted upward, beginning its long ascent toward interstellar space. Voyager 2 pressed forward, ready for the icy giants. By the mid-1980s, Voyager 2 already had a resume strong enough to secure its place in history. It had captured Jupiter's storms and moons, revealed Saturn's rings, and Titan's shrouded atmosphere. But the mission wasn't over. Ahead lay the ice giants, Uranus and Neptune, remote worlds that no spacecraft had ever visited, and none have visited since. To this day, Voyager 2 remains the sole emissary to those faraway planets, a lonely trailblazer charting paths no one else has followed. First came Uranus in January 1986. At first glance, the seventh planet looked deceptively simple. A pale turquoise sphere, smooth and almost featureless. It seemed like a world drawn in broad strokes, as though someone had taken a crayon to the solar system and called it a day. But Voyager's instruments revealed complexities beneath the calm. Uranus was unlike any other planet. It rolled around the sun on its side, tilted at nearly 98 degrees, as if knocked over in some ancient collision. Instead of spinning like a top, it spun like a ball, lazily rolling in its orbit, its poles alternately basking in decades of sunlight and decades of darkness. This extreme tilt created seasons unlike anything on Earth, strange, elongated cycles where sunlight could shine on one pole for 42 years before switching sides. The pale blue-green hue came from methane in its atmosphere, absorbing red light and leaving only cool tones behind. Beneath the tranquil appearance, Voyager detected faint weather patterns, subtle winds, and the promise of an atmosphere more active than it looked. Even Uranus's rings and moons had surprises. Voyager discovered that the planet's dark, narrow rings were shepherded by small moons, much like Saturn's system. Its larger moons, including Miranda, revealed landscapes, twisted and bizarre, with cliffs towering higher than Everest and patchwork surfaces that looked like Frankenstein worlds stitched together. What had seemed at first like a bland turquoise ball turned out to be a place of tilted oddities and strange geology. The discoveries reminded scientists that even the quietest-looking planet can hold secrets. Uranus wasn't flashy, but it was weird, delightfully, profoundly weird. And still, Voyager 2 pressed on. Farther out still, waiting in the shadows, was Neptune. Uranus had already upended expectations, but Voyager 2 wasn't done. Its sideways rotation and lopsided magnetosphere had shown that planets could be stranger than we dared imagine. And yet, farther out still, one more blue world was waiting, Neptune. It would take 3 more years of travel, 5 billion kilometers through the cold emptiness, before Voyager 2 reached the outermost of the classical planets. By August of 1989, more than a decade after launch, the little spacecraft finally arrived at its final planetary destination. What it saw was dazzling. From Earth, Neptune had been little more than a dim turquoise dot. Voyager revealed a vibrant, active world with an atmosphere as alive as Jupiter's, though in a very different palette. Its rich blue came from methane gas, which absorbed red light and scattered shades of blue. But beneath that beauty churned a place far more turbulent than expected. Voyager discovered massive storms raging across Neptune's face, including the now famous Great Dark Spot. Roughly the size of Earth, this swirling storm system roared with winds exceeding 1,300 miles per hour, the fastest ever recorded in the solar system. Supersonic gales tearing across a planet almost 30 times farther from the Sun than Earth. The sheer power of Neptune's weather baffled scientists. How could a world receiving so little sunlight generate such furious energy? The question remains unsolved even today. Voyager's instruments revealed more strangeness. Like Uranus, Neptune's magnetic field was tilted and offset, its poles not aligned with its spin, producing a magnetosphere that writhed and twisted in complex ways. The spacecraft picked up bursts of radio signals, evidence of the planet's dynamic interactions with the solar wind. It was as if Neptune were broadcasting its own chaotic music into space, a symphony in a key humanity had never heard before. But Neptune's greatest wonder was not the planet itself, but its largest moon, Triton. When Voyager 2 turned its cameras toward this frozen world, what it saw was astonishing. Triton orbited in the wrong direction, circling Neptune backward against the planet's rotation. That single fact suggested it hadn't formed there at all, but had been captured long ago, possibly a wandering body from the Kuiper Belt, pulled into Neptune's grasp. Triton was bitterly cold, yet far from dead. Voyager observed geysers erupting from its surface, columns of nitrogen gas and dust spraying miles into the thin atmosphere. This cryovolcanism, volcanoes of ice rather than fire, hinted at hidden internal heat. The surface was patchworked with strange terrains, smooth plains, ridges, streaks darkened by eruptions. Some regions looked as though they had been freshly repaved in geological time. Triton, distant and tiny, was unexpectedly alive. It even held a thin but detectable nitrogen atmosphere, making it one of the few moons in the solar system with such a feature. Along with Triton, Voyager discovered 6 new moons and Neptune's faint rings. These were not the grand, bright bands of Saturn, but dark, incomplete arcs, clumpy collections of particles circling the planet, like unfinished sketches. The farther out Voyager traveled, the stranger and less orderly the ring systems became, as though the neat beauty of Saturn had given way to eccentric experiments at the edges of the Sun's domain. With Neptune and Triton documented, Voyager's grand planetary tour was complete. No other spacecraft has since visited Uranus or Neptune. To this day, Voyager 2 remains the only emissary to have seen them up close, and what it revealed reshaped the way scientists understood the outer solar system. But the story didn't end there. After Neptune, there were no more worlds to aim for, at least none the spacecraft could reach. Voyager 2's cameras were eventually turned off to save power. Its mission transformed, shifting from planetary explorer to something more abstract, an interstellar traveler, drifting into the dark. Yet what it left behind was extraordinary. Uranus and Neptune had gone from distant blue smudges to fully realized worlds, one tipped on its side, the other storming with supersonic winds. Triton spouted icy geysers. Rings and moons played out gravitational dances no one had ever suspected. From billions of miles away, a probe built in the Disco Decade had rewritten the encyclopedia of the solar system. And then, woven through all of this, was a quieter story. The story of a golden disk strapped to the side of each Voyager, a gift not for us, but for the stars. Long before music streaming or playlists, humanity had made a mixtape, not for each other, but for whoever might someday find it in the infinite dark. It was called the Golden Record, and today it is still out there, turning slowly, waiting for a listener. The idea was born from Carl Sagan and a small group of collaborators who realized that Voyager would leave the solar system entirely. If these spacecraft were destined to wander forever, why not attach a greeting? Not because aliens were likely to find it. The odds were vanishingly small, but because of what the gesture meant. A way of saying, we were here. We thought, we dreamed, we sang, and we hoped. The record itself was a 12-inch disc of gold-plated copper encased in aluminum, with a needle and simple instructions engraved on how to play it. A time capsule, an art project, a cosmic postcard. And it had to capture, in just over an hour of sound and a few hundred images, the essence of Earth. No pressure. The team worked quickly, with only months to gather the contents and prepare the records before launch. They weren't just scientists. They became curators of human experience. Greetings in 55 languages were recorded, from Akkadian, the tongue of ancient Mesopotamia, to Wu, a Chinese dialect. Some messages were formal, some playful. One in English simply said, "Hello, from the children of planet Earth," spoken in the clear voice of a child. Simple, direct, moving. The greetings were just the beginning. The team filled the record with the natural sounds of Earth. A sonic portrait of our world. Waves crashing on a shore. The crackle of thunder. The rustle of wind through trees. Birdsong. The laughter of children. A kiss. Even the deep, haunting song of a humpback whale. These choices weren't random. They were meant to carry emotion, not just information, to make whoever heard them feel what it's like to live on Earth. And then came the music. This part truly was a mixtape, curated with care to reflect humanity's diversity. Classical pieces like Bach's Brandenburg Concerto, a gamelan ensemble from Indonesia, a Navajo night chant, a Japanese shakuhachi flute melody, a Peruvian wedding song, Louis Armstrong's blues, filled with longing and warmth, and Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless blues moan that Carl Sagan said captured the human condition more than any speech ever could. Pain, hope, yearning, all carried in sound. The Beatles had even offered Here Comes the Sun, but copyright complications blocked its inclusion. In the end, not even the most optimistic gesture of cosmic goodwill could escape Earth's paperwork. Perhaps that in itself was a fitting reminder of our humanity. Creativity always accompanied by complications. The Golden Record also carried images, 116 of them, encoded in analog form, a visual gallery for the cosmos. There were photographs of landscapes, forests, mountains, deserts, rivers, animals of every kind, elephants, insects, birds, fish, people eating, dancing, nursing their children, working in fields, diagrams of DNA, pulsar maps, mathematical equations, depictions of human anatomy, even a portrait of Earth itself from space. It was both a scrapbook and a primer, offering anyone who found it a glimpse of our planet and the creatures that lived here. One of the most intimate inclusions was a recording of brainwaves, those of Anne Druyan, a member of the production team who would later become Carl Sagan's wife. Electrodes traced her thoughts as she meditated on love, history, humanity, and the planet we share. Encoded into the record, her mental fingerprint still travels outward, a fragment of consciousness cast into the stars. Somewhere billions of miles away, her hour of thoughts continues its journey, a ghostly whisper of human intimacy floating forever. The cover of the record bore instructions on how to play it, etched in symbols and diagrams. Pulsar maps marked Earth's location. A drawing showed how to mount the needle. The hope was that any being advanced enough to find the record would also be clever enough to decipher its code. Some critics joked we had given the galaxy our return address, but Carl Sagan saw it differently. He believed that if a civilization was capable of reaching Voyager, they were capable of deciding their own intentions. The record wasn't a beacon, it was a greeting card. 2 copies were made, one for each spacecraft. Today, they are the farthest human-made objects in existence, each carrying its golden disk, slowly turning as they drift through the interstellar dark. They do not broadcast. They do not blink. They simply are. And in their silence, they carry a promise that humanity once reached outward and chose to represent itself not only with data, but with music, laughter, and the sound of waves. It is easy to dismiss the golden record as sentimental, even naive, but that misses its purpose. It wasn't about probability. It was about identity, about saying that exploration is not just charts and measurements, but meaning, that we are not only a species of engineers, but also of storytellers, dreamers, poets. Carl Sagan once called it a bottle cast into the cosmic ocean. The odds of it being found may be minuscule, the chance of it being understood smaller still. But the act of sending it, that choice, was profound. Somewhere right now, billions of miles away, those records still spin. They are not shouting into the void, but whispering. A quiet reminder that once, on a small blue world, there lived a species that made music, told stories, laughed, kissed, loved, and looked up at the night sky with wonder. When Voyager 1 and Voyager 2 left Earth in 1977, our knowledge of the solar system was incomplete. The outer planets were still half mysteries, sketched with telescope blurs and speculation. But over the decades that followed, the Voyagers transformed them from distant question marks into vivid exclamation points. Volcanoes on Io, oceans under Europa, Titan's haze, Saturn's haunted spokes, Uranus tipped on its side, Neptune's supersonic storms, Triton's icy geysers, a gallery of discoveries that no one could have predicted, captured by machines built with 1970s technology and determination. The planetary encounters may have ended, but the Voyagers themselves kept going, and as they drifted toward the edge of the sun's influence, their mission shifted once again. They became not just planetary explorers, but emissaries to the stars. Long before Voyager reached the edge of the solar system and captured that legendary farewell image, its earlier encounters had already revealed a solar system far stranger and livelier than we imagined. The moons, once thought to be frozen, cratered relics, turned out to be worlds of their own. They weren't just satellites circling their planets like passive companions. They were characters with dramas, geologies, and histories, each adding depth to the planetary story. Io, for instance, shattered every preconception of what a moon could be. Before Voyager's cameras focused on it, most scientists expected nothing more than a cratered body, maybe some icy ridges. Instead, they saw the solar system's most volcanic world. Plumes of molten material erupted into space, soaring hundreds of miles above the tortured surface. These weren't minor trickles or puffs of steam. They were geysers of fire, towers of sulfur and lava, reshaping the landscape in real time. Io looked less like a moon and more like a cosmic forge, painted in sickly yellows, sulfurous reds, and glowing oranges. Its face seemed constantly rearranged, as though the moon itself was restless, forever tearing itself apart and putting itself back together again. The cause of this relentless fury was not hidden beneath the surface, but written into Io's orbit, locked in a gravitational tug-of-war with Jupiter and its siblings Europa and Ganymede. Io is constantly pulled and stretched. That squeezing heats its interior until rock itself melts and bursts forth in furious eruptions. Earth's moon may hang quietly above our skies, but Io was a tantrum made of stone, forever proving that even a small world can hold astonishing power. And then came Europa, which couldn't have been more different. Where Io was volcanic chaos, Europa was icy calm, at least on the surface. Voyager revealed a smooth, bright crust, marked by long, dark lines. These fractures weren't scars of impact or mountain ridges. They were cracks in an ice shell, evidence that the frozen crust might be floating on a liquid ocean beneath. The thought was staggering. Beneath that cold white shell could be more water than all of Earth's oceans combined, hidden away, warmed by tidal flexing, and perhaps hospitable to life. The mere suggestion of such a sea shifted Europa from background moon to one of the most tantalizing places in the entire solar system. Ganymede and Callisto also stepped into the spotlight. Ganymede, the largest moon in the solar system, even larger than Mercury, displayed grooves and ridges that hinted at past tectonic shifts. It wasn't just a lump of ice and rock, but a world with a magnetic field, the only moon known to have one, and a complex internal history. Callisto, on the other hand, wore its age openly. Covered in ancient craters, it was like a cosmic scrapbook, its battered surface preserving billions of years of solar system history. Each crater was a reminder of how violent the cosmos can be, and how some worlds bear their scars forever. Saturn's moons, too, had their secrets. Enceladus, though small and unassuming, gleamed with a brightness that hinted at a youthful surface. Voyager didn't see the geysers later revealed by Cassini, but it provided the first clues. Its reflective surface, its suspicious lack of craters, suggested that something beneath the ice was reshaping it, refreshing it, whispering of hidden activity. And then there was Titan, Saturn's largest moon, wrapped in a thick, hazy atmosphere that concealed its face. Voyager's instruments pierced that haze just enough to measure it. Mostly nitrogen, laced with methane, and thicker than Earth's air, Titan's atmosphere was unique. It was the only moon with such an envelope, a miniature planet in its own right, and one that seemed to echo the chemistry of early Earth. Voyager couldn't see Titan's surface, but it left scientists captivated, wondering what strange landscapes might lie beneath the haze. And the surprises didn't stop with Jupiter and Saturn. Farther out, Voyager 2 revealed the icy moons of Uranus and Neptune. Miranda, a small satellite of Uranus, looked like a patchwork experiment. Giant cliffs, broken ridges, and chasms deeper than the Grand Canyon. Its scarred face suggested violent upheavals, perhaps even a history of being torn apart and stitched back together. Triton, Neptune's largest moon, was equally astonishing. It orbited backwards against Neptune's rotation, a sure sign that it hadn't formed there, but had been captured. And it wasn't dead. Voyager 2 saw geysers of nitrogen erupting from beneath its frozen crust, proof of activity in one of the coldest, most distant places in the solar system. But the moons were only half the story. The planets themselves revealed secrets that had eluded centuries of earthbound observation. Jupiter, always known for its great red spot, showed itself as a world of furious weather. That massive storm, large enough to swallow Earth whole, rotated with an elegance that was mesmerizing. But Voyager's real revelation was that Jupiter's entire atmosphere was alive with movement. Jet streams whipped around the planet. Smaller storms swirled and merged. Clouds stacked in layers of vivid color. Jupiter wasn't a giant, static gas ball. It was a dynamic machine of weather, a theater of motion and power, unlike anything we had imagined. Saturn, too, proved to be more than the graceful golden world seen through telescopes. Voyager's instruments uncovered faint cloud patterns, lightning, and auroras dancing at the poles. Its shape, flattened at the poles by rapid rotation, came into sharp focus. And then, of course, there were the rings. Those shimmering bands that had long enchanted stargazers turned out to be far more complex than we'd ever guessed. Voyager showed us that Saturn's rings weren't solid sheets, but intricate structures made up of countless icy fragments. They were layered into ringlets, braided and divided by gaps, sculpted by the gravity of tiny shepherd moons. Among the strangest discoveries were the spokes, ghostly shadows drifting across the rings, appearing and vanishing like phantoms. No one had expected them, and even now they remain partly mysterious, thought to be tied to Saturn's magnetic field and charged dust particles. Voyager turned the rings from a celestial accessory into a laboratory where gravity, magnetism, and matter performed a dance so delicate and complex that even now scientists puzzle over it. And Saturn's rings weren't unique after all. Voyager revealed that Jupiter, Uranus, and Neptune all had rings of their own. Faint, thin, subtle, but undeniably there. What had once made Saturn stand apart now became part of a broader story. Rings weren't an exception, they were a rule. If the moons and rings showed us drama, it was the magnetic fields that added a sense of mystery. Voyager's magnetometers revealed planetary personalities hidden in invisible lines of force. Jupiter's magnetic field was immense, extending millions of miles into space, trapping radiation, particles, and energy in belts so intense they dwarfed anything near Earth. The planet wasn't just a giant ball of gas. It was an electromagnetic powerhouse, shaping space around it on a colossal scale. Saturn's magnetic field, by contrast, was elegant and symmetrical, nearly aligned with its axis of rotation. Still, it pulsed with radio emissions, created auroras, and hummed with interactions between the rings and the planet's own magnetic environment. But the real curveballs came from Uranus and Neptune. Their fields were tilted, lopsided, and off-center, producing magnetospheres that wobbled and shifted unpredictably. These weren't quirks, they were puzzles, forcing scientists to rethink the very models of how planetary dynamos work. Voyager reminded us that nature rarely follows the tidy rules we expect. Beyond magnetism came the atmospheric data, layers upon layers of discovery. With spectrometers and infrared sensors, Voyager traced chemical fingerprints in planetary skies, hydrogen, helium, methane, and more. It measured cloud heights, charted temperatures, and recorded the way sunlight and heat rippled through alien atmospheres. Even faint gravitational variations told stories. Differences in planetary mass distribution, whispers of structure buried deep below the clouds. Plasma detectors captured how the solar wind tangled with planetary fields, turning invisible storms into measurable patterns. Decades later, scientists are still sifting through that data, writing papers from signals first carried home in the late 1970s and 80s. And then there were the moons. Dozens of them, many previously unknown, suddenly became part of the cosmic family album. They weren't just dots in a chart anymore. Voyager gave them faces, surfaces, stories. From Miranda's broken puzzle of ridges to Triton's frozen geysers, from Ganymede's grooved plains to Titan's hazy shroud, they revealed themselves as characters in a narrative far richer than anyone had dared expect. The outer planets weren't lonely giants after all. They were hosts to bustling, complicated systems filled with diversity and surprises. What tied all of this together wasn't just the discoveries themselves, but the way Voyager accomplished them. With less computing power than a pocket calculator, relying on tape recorders, analog commands, and patient radio transmissions, the spacecraft managed to rewrite textbooks and rewire imaginations. Every photo, every byte of data was the product of resilience, careful planning, and a design philosophy that valued simplicity and durability over flash. Voyager's engineers built a machine that could endure and endure it dig. By the late 1980s, the planetary grand tour was drawing to a close. Voyager 1 had already passed Saturn and turned northward, leaving the solar system's plane behind. Voyager 2 had pushed even farther, visiting Uranus and Neptune, completing a journey no other probe has repeated. The missions could have ended there, proud and complete, but Voyager wasn't finished. In 1990, NASA granted Carl Sagan's long-requested idea, one final act of perspective. On Valentine's Day of that year, Voyager 1, already billions of miles away, turned its cameras back toward the inner solar system. It was a risky maneuver. Pointing the optics near the sun could have damaged them, but the cameras were already scheduled for shutdown, and this last gesture was worth the gamble. The spacecraft rotated, aimed, and clicked. The result was a mosaic of the solar system, a family portrait stitched from 60 images covering 32 degrees of sky. Venus, Saturn, Uranus, Neptune, Jupiter, and Earth appeared as faint points of light. Mercury was lost in the sun's glare, and Mars didn't show clearly. But among all the tiny dots, one stole the show. Earth, a pale blue speck, suspended in a shaft of scattered sunlight, smaller than a pixel, almost invisible, easy to overlook. Yet it was us. When Carl Sagan reflected on that picture, he transformed it from a photograph into philosophy. In his book, Pale Blue Dot, he wrote of that pixel, "That's here, that's home, that's us." He reminded us that every person who has ever lived, every triumph, every tragedy, every act of kindness, and every cruelty, all of it unfolded on that tiny dot. He urged us to see beyond pride and conflict, to understand our fragility, to preserve the only world we've ever known. From billions of miles away, Earth was reduced to humility, but also elevated to meaning. That image was Voyager's final photograph, its farewell to visual exploration. The cameras were shut down soon after. From then on, Voyager would no longer capture light. It would listen, measure, and whisper back data as it slipped into the long silence of interstellar space. But that last look home gave humanity something more profound than any storm or moon: perspective. The pale blue dot became an icon, not because it was beautiful, but because it was true. It reminded us that exploration isn't only about what's out there, but about what looking outward teaches us about ourselves. Voyager had shown us the storms of Jupiter, the rings of Saturn, the tilt of Uranus, the winds of Neptune, and the secrets of their moons. But in its final glance, it showed us something even more important. That all of it, all the wonder, all the discovery, was tied to a fragile world adrift in the dark, a world worth cherishing. And as Voyager continued on, past the reach of planets, past the warmth of the sun, into the quiet unknown, it carried with it not just instruments and a golden record, but the story of us. And maybe, Just maybe, looking back from such a staggering distance helps us see what's right in front of us a little more clearly. If the solar system were a house, we humans would be somewhere in the living room, comfortably near the hearth of the sun, surrounded by familiar neighbors, with the asteroid belt and the giant planets decorating the walls. But like any house, there comes a boundary, a place where the shelter ends and the wilderness begins. For Voyager 1, that threshold was the heliopause. Crossing it wasn't just another milestone in a long journey. It was the moment humanity first stepped outside the sun's protective bubble and into the galaxy beyond. To understand the heliopause, picture the sun not merely as a glowing ball of light, but as a cosmic campfire. From its surface, it releases more than warmth and illumination. It breathes out a steady gale of charged particles, a solar wind that rushes outward in all directions. That wind carves a vast, invisible bubble around the solar system, known as the heliosphere. Inside that bubble, the sun rules. Its magnetic field dominates. Its particles flood the space, and everything within dances to its rhythm. But eventually, inevitably, the sun's breath runs thin. The gale weakens as it collides with the thin, cold mixture of gas, dust, and radiation that fills the galaxy, the interstellar medium. The boundary where the solar wind finally yields is the heliopause. Beyond it, the sun's influence fades, and the interstellar sea takes over. In theory, the concept is neat and simple. In practice, it is messy, indistinct, and alive. There is no glowing signpost announcing, "Now leaving the solar system." The boundary shifts and ripples, expanding and contracting with the sun's cycles, with bursts of solar storms, with unseen currents of the medium outside. For decades, scientists had guessed at its distance, modeled its behavior, and dreamed of reaching it. But no spacecraft had ever made the crossing until Voyager. In August 2012, NASA confirmed what once seemed like science fiction. Voyager 1 had crossed the heliopause. After 35 years of travel, it had left the realm of the sun and entered interstellar space. Humanity had, at last, sent something beyond the neighborhood of its birth. But how can you be certain of such a crossing when there is no door, no wall, no boundary line to see? Voyager could not send back photographs of a frontier. Instead, the clues came from the particles and fields surrounding it. Inside the heliosphere, the spacecraft had always been bathed in solar particles, fast protons and electrons shed by the sun. But as it pushed outward, those dwindled, replaced by a rising tide of cosmic rays. Particles born in distant supernovas and accelerated across interstellar distances. That swap was the first hint. The magnetic field told another part of the story. Scientists had expected the field to flip direction once Voyager left the heliosphere, but it didn't, at least not in the obvious way models had predicted. Instead, the data showed subtle changes that puzzled researchers and sparked debates. Had Voyager truly crossed? Or was it still clinging to the last threads of the sun's domain? The answer arrived in the form of a stroke of cosmic luck. In March 2012, the sun belched out a coronal mass ejection, a titanic wave of plasma hurtling into space. More than a year later, that shock wave finally caught up to Voyager. When it did, Voyager's instruments recorded the surrounding plasma, vibrating like a drum. By measuring the frequency of those oscillations, scientists could calculate the density of the medium around it. The result was unambiguous. The density had jumped 40-fold. Voyager was no longer inside the solar bubble. It was drifting through the true interstellar medium. The debate was over. That moment, quiet, data-driven, easy to overlook, was among the greatest achievements in the history of exploration. For the first time, a machine built by human hands had left the sun's sphere of influence. Voyager had become interstellar. Still, words matter. Voyager 1 hadn't technically left the solar system in every sense. The sun's gravity extends far beyond the heliopause, deep into the distant Kuiper belt, and out toward the theoretical Oort cloud, a vast shell of icy bodies that may stretch halfway to the nearest stars. Voyager won't reach even the inner edge of that cloud for another 300 years, and it won't exit entirely for 30,000. But in every way that counts, in plasma, in radiation, in magnetic dominion, Voyager was no longer a solar system probe. It was a galactic traveler. Voyager 2 followed suit in November 2018, slipping across the boundary on a different path, confirming what Voyager 1 had first revealed. For the first time, humanity had not one, but two emissaries, sending back whispers from beyond the heliosphere, in a science often starved for repeat experiments. Having two explorers cross into interstellar space was nothing short of miraculous. Crossing the heliopause wasn't dramatic in a cinematic sense. No glowing walls, no cosmic gates, no alien vistas. What the spacecraft found was emptiness, emptier, colder, stranger than expected. But that emptiness hummed with low-frequency plasma waves. It bristled with magnetic currents stretching across light years. It was not silent, but subtle, a new kind of frontier where the sun's song was faint and the galaxy's music took over. And symbolically, the crossing was even greater. For millennia, humans had looked up at the night sky and imagined traveling to the stars. In 2012, one of our creations actually began that journey. Not with speed or glamour, but with patience, persistence, and a quiet refusal to stop. Voyager had become more than a planetary mission. It had become an interstellar odyssey. Voyager's entry into interstellar space wasn't marked by fireworks, but by persistence. Decades after launch, it was still whispering across billions of miles. Its signal, weaker than the hum of static on an old television, still reached Earth through the enormous dishes of NASA's Deep Space Network. By then, light itself took more than 17 hours to make the one-way trip from Voyager 1 to us. And yet, the data arrived, sparse, patient, but steady, telling us about cosmic rays, plasma density, and magnetic turbulence in regions no other probe had ever touched. It's humbling to remember what Voyager was originally built for. Its mission life was designed for just 5 years, long enough to reach Jupiter and Saturn, take some photographs, and beam back data. Anything beyond that was considered a bonus, and yet, those temporary machines have endured for nearly half a century, outliving expectations and even the people who built them. That endurance hasn't been effortless. Voyager's power comes from radioisotope thermoelectric generators, RTGs, which convert the heat of decaying plutonium into electricity. At launch in 1977, each spacecraft had about 470 watts of power to spend. Today, they have less than half that. With each passing year, the RTGs grow weaker, forcing engineers to make painful choices. Heaters are shut off. Instruments are silenced. Subsystems are powered down one by one. It is like tending a dimming lantern on a long night, keeping the flame alive as long as possible by feeding it sparingly. The sacrifices have been constant. Voyager's cameras, which once showed us the volcanic fury of Io and the icy mysteries of Titan, were switched off decades ago. No new pictures will ever come. What remains are instruments that measure magnetic fields, plasma waves, and cosmic rays, The tools most useful for exploring the space between the stars. Those few remaining sensors are the heartbeat of the mission, still sending science home. Even as its power dwindles, Voyager continues to surprise us. In 2020, Voyager 2 went silent for months when its link to Earth was interrupted during maintenance on the giant dish in Australia, the only antenna positioned to talk to it. When the dish came back online after 8 long months, Voyager 2 answered immediately, faint but clear, carrying on as though nothing had happened. In 2023, engineers faced another scare when Voyager 1 began transmitting corrupted data, the result of a likely memory chip failure. After months of detective work, the team devised a workaround and beamed it across the Gulf of Space. More than a day later, the spacecraft acknowledged the fix. Its systems back in order. Each recovery is a reminder that even across impossible distances, a conversation is still possible. But the reality cannot be denied. Sometime in the next few years, the RTGs will no longer produce enough electricity to power even a single instrument. Systems will go dark. Finally, even the transmitter will fall silent. There will be no grand finale, no dramatic failure, just a gradual fading into the quiet. And yet, the end of contact is not the end of the journey. Long after Earth loses their signals, the Voyagers will continue their flight. Voyager 1, moving at over 38,000 miles per hour, is destined to pass within a couple of light years of a faint star called Gliese 445 in about 40,000 years. Voyager 2 will head in another direction, skirting between the stars without a particular destination. Neither is aimed at a known system, and neither will ever return. They will simply drift, silent and intact, for millions of years. They will carry with them their most human cargo, the golden records, those gilded time capsules of music, images, and greetings from Earth. The odds of anyone finding them are slim, vanishingly small. But the records are there, attached to the spacecraft, turning endlessly in the void. They will outlast continents, languages, even civilizations. And if ever discovered, they will whisper, "We were here, and this is who we were." For now, though, they are not relics, but living missions. Their signals still reach us, though faint. Their data still informs our science. Their resilience still inspires us. These twin probes, designed in the age of punch cards and cassette tapes, continue to be humanity's farthest and longest-running explorers. The Voyagers remind us that exploration is not always dramatic. Sometimes it is quiet, slow, and almost invisible, but it endures. Their journey shows us the value of persistence, of building carefully, of daring to send something fragile into the most unforgiving wilderness and trusting it to endure. They are not only spacecraft, they are symbols. Someday soon, the last bit of power will drain, and the deep space network will fall silent in its listening. When that happens, Voyager will no longer speak, but it will not be gone. It will continue forward, twin emissaries adrift in the galaxy, carrying messages, memories, and the proof that a species on a pale blue dot once looked outward and chose to send its voice into the dark. Even in silence, Voyager will continue its mission, to travel, to endure, to remind us that we are explorers, and that we too are Voyagers. They remind us that exploration doesn't always need a finish line. Sometimes the act of reaching outward is itself the point. The Voyagers have become proof of that. Tiny beacons carried into a silence so vast that even the sun is reduced to a single dot, no brighter than a common star. And yet, despite the chill of the interstellar void and the creeping weakness of their power, they remain. Out there, two faint voices still whisper back home, carrying measurements and memories across an ocean of darkness. But time is catching up. If you could somehow lean close enough to hear them, not their signals, but the machines themselves, you might imagine the faint tick of power cells fading, a kind of cosmic heartbeat slowing with every passing year. From their beginning, the Voyagers drew strength from something unusual: radioisotope thermoelectric generators, or RTGs. Unlike solar panels, which fail once you drift too far from the sun's warmth, RTGs make their own power, converting the steady heat of plutonium-238 into electricity. It was an elegant solution to the problem of distance. Stable, reliable, and impervious to the shadow of deep space. But even perfection has limits. Plutonium decays at a steady pace, and with every year that passes, the heat weakens, the power dwindles. At launch in 1977, each RTG produced about 470 watts, just enough to light a handful of bulbs. By modern standards, it wasn't much, but it was steady, and it was all the spacecraft needed. Today, almost half a century later, that figure has fallen below half its original output, and there is no way to replenish it. Voyager is not a simple device. It is a symphony of instruments, heaters, transmitters, guidance systems, memory storage, each drawing its share of electricity. As the available supply shrinks, engineers must decide which pieces of the symphony must go silent. It's a slow process of triage, carried out over decades. First, non-essential instruments were powered down, even though they were still working perfectly. Then heaters in the coldest, most insulated corners were switched off. Piece by piece, the spacecraft was dimmed, like a house during a blackout. One light extinguished after another. By the late 1990s, several instruments were already gone. Others endured longer, measuring magnetic fields, detecting cosmic rays, or mapping plasma waves from beyond the heliosphere. Each shutdown brought a pang of loss to the mission team. Scientists saying farewell to companions that had traveled with them across entire careers. Some had worked with these instruments since they were graduate students. Watching them fall silent was like losing old friends. In 2023, Voyager 2's plasma science instrument was finally switched off. For years, it had measured the density and temperature of particles in interstellar space, painting the first detailed portrait of the medium between the stars. Its deactivation was necessary to conserve power, but the absence was felt deeply. Every decision like that is a small mourning, and yet each one also buys more time for what remains. And the spacecraft need warmth as much as power. Interstellar space is not merely cold. It is emptiness pressed toward absolute zero, where metal becomes brittle and electronics struggle to survive. The RTGs give off a little heat, but not enough. Small heaters placed strategically throughout the spacecraft keep valves and circuitry from freezing. They too consume precious energy, so over the years, heaters have been shut down. Some parts of Voyager now operate at temperatures far below what their designers ever imagined possible. Kept alive by insulation, clever routing of power, and sheer, stubborn resilience. Through all of this, the transmitters remain the crown jewel. Without them, no data reaches Earth. Keeping the signal alive is priority number one. But even this lifeline is under threat. Someday soon, NASA will be forced to choose between shutting down the transmitter or shutting down something else vital. When that day arrives, there will be no clever workaround, no borrowed watt from a backup circuit. There will be only silence. And yet silence has not come. Not yet. The team has found ways to stretch every fraction of a watt. In one instance, engineers tapped into a tiny onboard voltage regulator that had never been used before, reclaiming a sliver of extra power. It was not much, but it was enough to keep another instrument running. Each trick buys time, and time, at this stage, is Voyager's most precious fuel. Even in this twilight, the data keeps flowing. The Voyagers are still returning measurements of cosmic rays, plasma densities, and magnetic fluctuations, building a map of interstellar space no one else has touched. The data arrives slower now, smaller in volume, more carefully curated. But when it does arrive, it is pristine, ones and zeros etched in silence, carrying the story of a frontier beyond the sun's reach. What makes this remarkable is not just the longevity, but the fact that the Voyagers were never meant for this. Their original mission life was 5 years, just long enough to reach Jupiter and Saturn, take some snapshots, and retire. 5 years. Instead, they have endured almost 50. A spacecraft designed when disco filled the airwaves is still alive, still working, still rewriting science. That is not luck. That is engineering, care, and devotion from the people who have tended it. At NASA's Jet Propulsion Laboratory, a small team still watches over them. Commands are written, double-checked, and then transmitted with care across the Gulf. At Voyager 1's distance, a message takes 22 hours to arrive, and another 22 to confirm whether it worked. Imagine troubleshooting your car. If every message to the mechanic took 2 days, that's the level of patience required. And the engineers do it because they care. Because the spacecraft has become more than a machine. It is a legacy. They know the end is coming. Professionally, they've accepted it. Emotionally, it's harder. Some of them have dedicated their entire careers to these twin spacecraft. Others inherited the responsibility from earlier generations, carrying the torch as new hands took the controls. Each new fix is not just a technical challenge, but an act of stewardship. A way of giving the Voyagers one more year, one more season, one more message to the stars. Even as their strength wanes, the Voyagers still carry something more enduring than instruments or sensors. The golden records. Each disc is bolted to the side of its spacecraft, silent, gleaming faintly in starlight, a kind of eternal message in a bottle. They will outlast the power supplies, the transmitters, and even the memory of their caretakers on Earth. Long after the spacecraft fall silent, those records will remain, drifting endlessly through the Milky Way. And every so often, it's impossible not to wonder, what if someone, somewhere, someday, actually finds one? Frozen relics gliding in the dark. To stumble upon one would require a civilization not only advanced enough to notice, but also curious enough to investigate. And yet, if such a discovery did happen, what might they make of it? Picture an alien laboratory, where scientists, in whatever form they take, have just unbolted the golden disk from the spacecraft. They study its surface, noting the curious engravings, the diagrams etched into its jacket. At first glance, it might look like little more than a decorative artifact, until they realize the markings are instructions, an invitation. The hydrogen atom diagrams, the pulsar map, the lines of mathematical notation, all carefully chosen in the hope that physics is a universal language. To us, the steps are obvious. Assemble the stylus, spin the disk, decode the sounds and images. It might be the ultimate cosmic puzzle, like trying to assemble furniture without the manual, but infinitely more tantalizing. If they succeed, they would hear music. And what music it would be! Chuck Berry's Johnny Be Good, with its frenetic guitar and uncontainable joy, placed alongside Bach's Brandenburg Concerto, Senegalese drumming, Navajo chants, Bulgarian folk songs, Indonesian gamelan, and the mournful slide guitar of Blind Willie Johnson. This mixtape is a celebration of diversity. To them, it may sound chaotic, alien, or oddly familiar in ways we cannot imagine. They may not even have ears. They might sense vibrations through another medium entirely. And yet, through rhythm and repetition, they might glimpse something fundamental. That humanity was a species capable of expression, emotion, and beauty. Then come the sounds, natural recordings stitched together into a kind of auditory collage. The crash of waves against a shore, the crackle of thunder, wind rushing through trees, the gallop of a horse, the laughter of children, the sound of a kiss, a Saturn V rocket roaring to life. To us, these are ordinary fragments of life. To them, they may be incomprehensible at first, but perhaps with time, they would piece it together. Maybe they'd argue about it. The high-pitched squealing, communication? No, emotional bonding. The wet smacking, nutritional ritual? Possibly. And the wail? Clearly a philosopher. The thought of alien analysts debating the meaning of a baby's cry or a blues riff is both humbling and delightful. The greetings add another layer. 55 languages, from ancient Sumerian to modern Mandarin. Some are formal, others playful. The English greeting, delivered in the clear voice of a child, is perhaps the most moving. Hello from the children of planet Earth. No embellishment, no poetry, just simple honesty. And perhaps that is what makes it timeless. And then there are the images, 116 in total, encoded into the grooves of the record. They show people eating, dancing, giving birth, holding hands. Animals, plants, landscapes, diagrams of DNA, maps of Earth, even a supermarket aisle. To us, these snapshots are mundane, everyday glimpses of life. To an outsider, they might look like documentary footage of a strange, carbon-based civilization that once thrived on a moist blue planet. Strange, yet unmistakably alive. Among the most poetic inclusions is something invisible to the eye. Brainwave data recorded from Anne Druin, who meditated on the history of life and the experience of falling in love. To us, it's a hauntingly intimate gesture, a heartbeat of thought, preserved as electromagnetic traces. To someone else, it might look like erratic pulses and meaningless peaks. Or perhaps, just perhaps, they would recognize it as what it truly is, a mind reaching outward, carrying love across the cosmos. Of course, there's every chance that if the Voyagers are ever found, their records will be dismissed as curiosities. Maybe the aliens will glance at them briefly, shrug in indifference, and return to whatever incomprehensible work occupies their time. But the point was never about who would find it or whether they would understand. The point was that we sent it, that we chose, as a species, to take a once-in-a-lifetime opportunity and fill it not with weapons or warnings, but with laughter, music, greetings, and the sounds of our world. It was never about the odds, it was about the gesture. Carl Sagan himself described it as casting a bottle into the cosmic ocean. Maybe it will never be found. Maybe it will never be understood. But in sending it, we made a statement about who we are, or at least who we aspire to be: curious, expressive, capable of kindness and creativity. A species that looked up at the night sky and wondered what it might mean to not be alone. That choice matters. It means that somewhere, billions of miles from home, two little spacecraft drift silently on, each carrying a golden disk that tells our story. They are ghost ships now, or soon will be, but even when their signals fade, they will still hold within them the laughter of children, the cry of a baby, the songs of whales, the voice of a child saying hello, and the echo of human love captured in a heartbeat. And so the Voyagers remind us that sometimes the smallest gestures, the simplest signals, carry the loudest echoes. Long after the instruments dim and the transmitters fall silent, those records will remain, waiting, turning, enduring. A quiet promise written in gold that once, on a tiny blue dot orbiting a yellow star, a species called humans lived, dreamed, sang, and said hello to the stars. That belief that someone out there might one day care enough to listen is what gives the golden record its power. The truth is, the message was never really meant for aliens. It was meant for us. It was our own declaration, frozen in gold, that said, this is who we were. We tried to understand. We tried to reach out. We made something beautiful, and we sent it into the dark. Even if no one ever finds it, even if those records drift untouched for 1 billion years, it matters simply because they exist. They are still out there, still spinning, still whispering, still carrying hope. It's hard to think of a mission that has lasted longer, traveled farther, or touched more hearts than Voyager. Launched in the late 1970s with little more than determination, slide rules, and a dream. These twin spacecraft weren't just explorers. They became ambassadors, archivists, even accidental poets. While they continue their slow journey into interstellar space, their echoes are felt most strongly here at home. Voyager's legacy didn't end with its last planetary flyby. If anything, that's when its true influence began. It lit a spark, not only among scientists, but across the imagination of the entire planet. The discoveries it brought back reshaped how we think about exploration. They widened our perspective. They showed us that the universe is richer, stranger, and more dynamic than we had dared imagine. For planetary scientists, Voyager was a revelation. Before it, the outer solar system was mostly speculation. Fuzzy telescope images, mathematical estimates, cautious sketches in textbooks. Voyager transformed those question marks into living portraits. Moons that had been assumed to be cold, cratered husks, revealed themselves as geologically alive. Io boiled with volcanism. Europa whispered of hidden oceans. Ganymede displayed its grooves. Callisto its ancient scars. Rings appeared not only around Saturn, but also Jupiter, Uranus, and Neptune. And everywhere, magnetic fields twisted in unexpected ways, reshaping our theories. In short, Voyager redefined what was interesting in the solar system. For decades, Mars had been the focus of habitability and intrigue. Voyager widened the stage dramatically. Suddenly, moons became candidates for life. Gas giants were no longer just balls of gas. They were weather machines, laboratories of storms, canvases painted with complexity. Rings weren't rare ornaments, they were universal structures. The entire framework of planetary science shifted, and exploration didn't stop there. Voyager's discoveries inspired new missions. Galileo went back to Jupiter, orbiting the giant and diving into its storms, probing its magnetic fields, and lingering around Europa with questions Voyager had first raised. Cassini followed at Saturn, a mission directly inspired by Voyager's fleeting encounters. Cassini did what Voyager could not. It dropped a lander on Titan, mapping its methane lakes and hazy skies. It skimmed through Saturn's rings, revealing structures Voyager could only hint at, before closing its mission with a spectacular dive into the planet's atmosphere. Even Juno, still orbiting Jupiter today, stands on Voyager's shoulders. It probes the gas giant's deep interior and magnetic field, with tools refined by decades of Voyager-inspired data. And when New Horizons flew past Pluto in 2015, many nicknamed it Voyager 3. Not officially, but spiritually. Like its predecessors, it was a single-shot flyby of a world we had never seen up close, carrying forward the same sense of wonder. Voyager also taught us what long-duration mission really meant. It showed that with careful engineering, precise navigation, and a little luck, a spacecraft could remain functional not just for months or years, but for decades. This reshaped how space agencies thought about planning and funding. It also reshaped careers. People who started as young engineers or scientists in the 1970s have spent their entire lives shepherding these spacecraft. Some have passed the torch to younger generations, who now continue the work of keeping the Voyagers alive. But Voyager's legacy isn't confined to laboratories. It also punched its way into culture, not with the fiery spectacle of Apollo or the rugged charisma of the Mars rovers, but with something quieter, deeper. It slipped into our collective imagination, like a story we tell around a campfire. Voyager appeared in films, novels, songs, and art. It was woven into Star Trek, the motion picture, where a fictionalized Voyager returns transformed into a sentient being. It was invoked in countless documentaries, quoted in books of poetry and science, and even sampled in music. The Golden Record, in particular, became iconic. Its grooves have been recreated in museums, celebrated in art projects, parodied on television, and imagined in science fiction as the first handshake between civilizations. Its sounds, whale songs, greetings, Bach, blues, have been replayed, remixed, and memorialized. The act of including it at all has become a symbol of humanity's optimism, of our ability to imagine being known. Voyager became more than a spacecraft. It became a metaphor, not for triumph or conquest, but for persistence, for quiet wonder, for the simple courage of looking outward. Its design itself feels almost quaint now. Analog tape recorders, wire-wrapped circuits, and computers with less memory than a key fob. No AI, no autonomy, no real-time adjustments. And yet, that very simplicity made them enduring. They were built to be resilient, to do their job without fuss, and to keep going. Decades later, they still are. Their durability has become legendary in engineering circles. Every line of code, every shielding plate, every antenna and magnetometer was crafted with foresight. And somehow it all lasted far beyond its warranty. Voyager was never built to dazzle with speed or clever tricks. It was built to endure, and endurance has a poetry of its own. Even now, with most instruments turned off and their cameras permanently silenced, the Voyagers remain storytellers. The data they send back today is not glamorous, no dazzling photographs of moons or rings, but it is profound. Their instruments still measure magnetic fields, charged particles, plasma densities. Numbers, yes, but numbers that whisper truths about a place we never thought we'd reach. Interstellar space. The signals are faint, fainter than a whisper from across a continent, but they arrive. Steady, patient, a stream of ones and zeros, traveling for over 20 hours across billions of miles to reach us. That is Voyager's final gift, the quiet persistence of science, the reminder that listening itself is an act of hope. Listening says, we believe there is something out there worth hearing, that even when the universe seems indifferent, we can tune in, wait, and learn. Voyager taught us that wonder doesn't always come as spectacle. Sometimes it arrives pixel by pixel, bit by bit, a blurry image of a distant moon, a rise in plasma density, the sudden realization that you've crossed into the galaxy itself. And then, of course, there is the golden record, a decision that wasn't about science at all, but about imagination. The record was never required. It added no data, solved no equations, and carried no instruments. It was simply a gift. Whale songs, laughter, greetings in Sumerian and Mandarin, Bach and Chuck Berry, a heartbeat, the brainwaves of a woman in love. None of it essential, all of it human. We could have sent warnings. We could have sent technical manuals or military broadcasts. Instead, we sent music and poetry, the sound of a kiss, the laughter of children. That choice may be Voyager's most enduring legacy. Not the storms it measured, not the magnetic fields it mapped, but the message it carried. We are a species of wonder. The act itself was remarkable. For the first time in history, we spoke first. The stars had always been silent. We broke that silence not with a shout, not with threats or fear, but with melody and greetings, with the raw beauty of our ordinary lives. It's humbling to realize that if Voyager is ever found, it will not be remembered for its engineering or science, but for the songs and whispers it carried into the night. Voyager also reshaped how we think about exploration. It taught us that reaching far is not just about planting flags or snapping photos. It is about asking better questions. How do magnetic fields behave at the edge of a star's influence? What happens when solar wind meets the interstellar medium? Could life exist beneath the ice of Europa or in the haze of Titan? Before Voyager, those questions were theoretical. After Voyager, they were grounded in evidence. And with every answer came more questions. That may be Voyager's most profound gift, the way it reminded us that curiosity never ends. The farther you look, the more there is to see. Now, after nearly half a century, the Voyagers are old. Their signals are fading. One by one, their instruments are shutting down. In the next few years, silence will come. No explosion, no dramatic finale, just a pause in a signal that never resumes. But silence does not mean loss. Even after their final whisper, Voyager 1 and Voyager 2 will continue on, quietly drifting among the stars. They will be our ghost ships, carrying the golden records as messages in a bottle, cast into a cosmic ocean. Perhaps no one will ever find them. Perhaps, millions of years from now, some distant civilization will. Either way, it doesn't matter. What matters is that we sent them, that we chose to represent ourselves with laughter, song, mathematics, and kindness, that we said hello first. And so, Voyager's journey is not only about what it discovered, but what it revealed about us. That we are builders, dreamers, singers, storytellers. That we sometimes make art not because we must, but because it feels right. That even at the edge of knowledge, we reach out not for conquest, but for connection. One day, soon, the Voyagers will fall silent. But silence is not the end. They will still be out there, moving slowly, eternally among the stars. They will still carry their records, still carry our words, our sounds, our heartbeat. They will still embody the moment when humanity decided to send beauty instead of fear, hope instead of silence. And maybe that's enough. Maybe that's all the legacy we need. Now, as this story comes to a close, I'll ask what I asked at the very beginning. Are you still awake? Still drifting among the stars with me? Or have you slipped into sleep, carried off by Voyager's gentle signal into dreams? Either way, thank you for joining this journey. Before you go, I'd love to know where you're listening from and what time it is where you are. Whether beneath the glow of a city skyline or racked in the quiet of a countryside, whether it's midnight or dawn, thank you for being part of this voyage. If you've enjoyed traveling through time and stars with me, consider leaving a like and subscribing to The Lazy Scientist. It helps more dreamers find their way here, and it helps keep the signal alive just a little longer. Until next time, rest well, stay curious, and remember, we spoke first.